Good morning, dear students. Welcome to this digital classes. This is your chemistry period, and as you know that nowadays we are doing our P block elements. Already we have finished this P block element in the last week. So if we will recapitulate the P block element, what is P block element that we studied? Those elements, their last electron enter in p orbital, and these have general configuration generally ns2 to np1 to 6, that is known as p block elements. And basically we have done in this particular class, that is we have done group number 15, 16, 17 and 18, in which group number 15 is nitrogen family, group number 16 is oxygen family, group number 17 is halogen family, and group number 18 is noble gas family. Okay, so what we have done from all these group 15, 16, 17 and 18, first we have done the general preparation, properties, then chemical and physical properties, periodic trends, anomalous properties of the first element of the group with the other family members, and we have done the important compounds of nitrogen, phosphorus from group 15, oxygen, sulfur from group 16, and chlorine from group 17, and xenon from group 18. Basically the most important question that is coming from structure type question. So these all things we have done from group 17, it is already finished. Group 13, 15 to 18, that is P block elements. Now we are going to start our next unit, that is unit 8, that is named D and F block elements. So let's start D and F block elements. So welcome, dear students. Today we are going to start our unit 8, that is D and F block elements. That is already we have done. It is the second series of the periodic table. One unit, that is unit 7, P block elements, already we have finished. So today we are going to do this D block elements. This is a general periodic table that you know, long form of periodic table, which is given by the Bohr and Moseley. So dear students, already we know we have done the S block elements. Then this periodic table has divided into 4 parts. S block elements, P block elements, then in between S and P there is a transition elements, that is D block elements, and in the bottom that 2 row of F block elements. So generally now S block elements we did in 11th class, P block elements we did in which 15, 16, 17 and 18 group we did. Now our focus is in this particular unit, that is unit 8. Unit 8 we are doing, the name of unit 8 is D block elements and F block elements. Both the group of elements we will do. Now generally if we will tell about the D block elements, let me little bit focus on this, zoom on this. So this is particular D block elements. So the D block of the periodic table includes all those elements of group 3 to group 12. It is including from group 3 to group 12, in which the d orbital are progressively filled in each of the 4 long periods. 1, 2, 3, 4. These 4 periods, the d blocks elements are progressive. Generally we studied the elements in a group like down the group, but in D block and F block we will study from left to right. Okay, like if boron, aluminum, gallium, indium, tellurium are the group of family of boron. So here we will study scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc, like this way from left to right. Okay, this is the one difference. And the element constituent F block elements, that is these are the F block elements from here to here. These are F block elements which is kept under the D block, and the origin of these F block are somewhere from here. Third group, group 3, period 6 and 7, that it is in between these. Okay, it is inside this, that's why it is called inner transition element, because these F block elements present inside the transition, that's why it is called inner transition elements. And the element that constituent F block, these are somewhere 4f and 5f orbital, which are progressively filled in latest 2 long periods. Okay, these elements are formal member of group 3 from which they have been taken or developed a separate F block and periodic table. Generally, the term transition elements are used for D block, and inner transition is used for F block elements. Okay, so that's why today we are going to start our this unit, that is D block and F block. The two series of the inner transition 4F and 5F are written separately outside the periodic table, which are called lengthenide and actinide series. These are also known as famously lengthenide and actinide series. So this series is of lengthenide series, and this series of yellow color series is of actinide series. Okay, so if we will take general configuration, general idea about the D block elements. So basically the D block elements are group number. Generally the D block elements are group number 4. You can see group number 4, group number 3, sorry, and period 4. Group 3, period 4. It starts from 4th period and from group 3. Okay, 3 to 12. So 3 to 12 are D block elements, in which generally 4 periods are there, and F blocks are in last to 6th and 7th period and in third group. Okay, which are generally found in the, so these are basically metals, and there are so many important properties of D and F block that we are going to start. So general properties of D block elements, which is transition elements, we will study.
D block elements is the collective name for the groups 3 to 12, in which the d orbitals are progressively filled in each of the 4 long periods. As the D block elements lie between the S and P block elements, they are also referred to as the transition elements. The F block elements, on the other hand, include the 4F and 5F series of elements, in which the 4F and 5F orbitals are progressively filled. They are often referred to as the inner transition metals because they involve the filling of the inner 4F or 5F subshells. There are mainly 3 series of transition elements. They are the 3D series, the 4D series, and the 5D series. The 4th series, the 6D series, which begins with actinium, is still incomplete. The first transition series includes the elements from scandium to zinc. The second transition series includes the elements from yttrium to cadmium. While the third transition series includes the elements from lanthanum to mercury. By definition, transition elements are those that have incompletely filled d orbitals either in their elemental state or in any one of their chemically significant oxidation states. Thus, the elements zinc, cadmium, and mercury, which have D10 configuration, both in their elemental and in their stable oxidation states, are not considered transition elements. The general electronic configuration of these elements is N-1 D1 to 10 NS1 to 2. This generalization has several exceptions, because the energy difference between the Ns and N-1 d orbitals is less, and the transition of electrons between Ns and N-1 d takes place readily. Furthermore, atoms of the d block elements try to fill their available d orbitals either partially with 5 electrons or completely with 10 electrons whenever possible. This is due to the fact that half-filled or completely filled orbitals impart greater stability to an atom because of the greater exchange energy. A consequence of this factor can be seen in the electronic configurations of chromium and copper in the 3D series. Chromium, for example, has a configuration of 3D5 4s1 instead of the expected 3D4 4s2. Copper, on the other hand, has an electronic configuration of 3D10 4s1 instead of 3D9 4s2. The properties of transition elements depend largely on their electronic configurations. Thus, with partly filled d orbitals, these elements exhibit certain characteristic properties, like display of a variety of oxidation states, catalytic properties, alloy forming ability, complex forming ability, formation of colored hydrated ions and salts, and para- and ferromagnetic properties. The precious metals like gold, platinum, and silver, and industrially important metals like iron, copper, and titanium form part of the transition elements. The electronic configurations of the d block elements differ only in the number of electrons in the d orbitals of the penultimate shell, while the number of electrons in the valence shell remains the same. Thus, they have many physical and chemical properties in common. Nearly all the elements exhibit typical metallic properties. Let us review some of them in detail. First, let us look at the metallic character. As the number of valence electrons in these elements is very small, all of them are metals. They are good conductors of heat and electricity. They exhibit metallic luster and are hard. They are malleable and ductile. They form alloys with other metals. They have one or more typical metal lattice structures as shown in the table here. Like beryllium and magnesium, with which they are isostructural, their structures deviate from perfect hexagonal close packing by elongation along the six-fold axis. Mercury is a shiny liquid at ordinary temperature. Melting and boiling points. The melting and boiling points of the transition elements are generally high. The melting points of 3D, 4D, and 5D transition metals are depicted in the figure here. As you can see, in any series, with the exception of anomalous values for manganese and technetium, the melting points first increase to a maximum at D5 configuration and then gradually decrease towards the end of the period. The high melting points of these elements are attributed to the participation of a greater number of electrons from n-1 d orbitals in addition to the ns electrons in the interatomic metallic bonding. Now let's look at the atomization enthalpies of these elements. These elements have high enthalpies of atomization. The trends in the enthalpies of atomization of these elements are shown in this graph. From the graph, you can see that they exhibit maxima at about the middle of each series. The maxima in each series indicate that interatomic interactions are stronger in half-filled d orbitals. It means that the greater the number of unpaired electrons, the stronger are the interatomic interactions and the stronger is the bonding between atoms. Consequently, the higher are the enthalpies of atomization. Enthalpy of atomization is an important factor in determining the standard electrode potential of a metal. Hence, metals with high standard electrode potential tend to be noble in their reactions. For example, copper, due to its high enthalpy of atomization, exhibits noble character. You will also note from the graph that the metals of the second and third transition series have greater enthalpies of atomization than the corresponding elements of the first series. This factor accounts for the occurrence of frequent metal-metal bonding in compounds of heavy transition metals. The atomic radii of elements in the 3D series are given in the table. You can see from the table that the atomic radii of the elements show a progressive decrease in radius with an increase in atomic number. This is due to the fact that an increase in the nuclear charge tends to attract the electron cloud inwards. You already know that d